Yeah. So in our last class, we have seen about intrinsic semiconductors, extrinsic semiconductors, and their properties, right? And their conducting properties. Oh, yeah. And also, we have seen about majority charge carriers and minority charge carriers. In this class, we are going to see about uh, a p-n junction, right? We have seen about p-type semiconductors and n-type semiconductors. In this class, we are going to see about a p-n junction and the electrical properties of a or maybe a current voltage characteristics of a p-n junction, right? A p-n junction is actually uh, uh, kind of, right? You have a p-type semiconductor and n-type semiconductor, both made up in a single piece of semiconductor crystal. Or we could say that on a p-type semiconductor, we can diffuse an n-type dopant to make a half of the semiconductor into n-type, right? So for example, right, this side be p-type and this side be n-type, right? N-type means we will have a lot of electrons, right? I would say, yeah, we will have electrons which are majority charge carriers, and then we will have some holes, right, which could be generated due to the thermal excitation, right? So yeah, maybe I have some more electrons, right? Meanwhile, at p-type we will have, right, majority of holes in the semiconductor, right, or more number of holes and a few electrons, right? So when I diffuse an n-type or dopant into a p-type dopant, there will be a p-n junction is occurs, right? So at this interface, as you all know, the negatively charged electrons will jump and then fill the holes in the opposite side, something like this, right? So I would say, yeah, it will create a region where you have, yeah, something like a charge free region. Meantime, yeah, there will be holes and they can recombine as well, right? So I can say that when the electron fill the hole, there will be a negatively charged ion is being generated, and when an electron is being left from the n-type, I would say a positively charged ion is being created in the n-type, right? Due to the creation of these oppositely charged ions, right, a potential difference will be developed within this region, right? So that is called as VD, and you can see that there are no free charges within this region, right? All the holes will be recombined with the electrons, and hence they created a negative ion, and the left electrons will create a positive ion these sides, right? So I could say that the charges have been depleted in this region, right? So this region can be called as a depletion region, right? A charge depleted region, right? Okay, so this is a p-n junction at ground state or at zero bias state, right? So let's see how this p-n junction behaves whenever it is connected to an external power supply, right? So let this p-n junction, right, is connected to a battery, right? So n-type, I would say it as a minus terminal, right? And p-type, I would say it as a plus terminal, right? So cathode and anode, or minus or plus. First, I will connect the minus terminal to the minus terminal of the battery, and then the P type to the positive side of the battery. Right now, which means I am virtually introducing a lot of holes in this side, right? And then a lot of electrons in this side. Clear. So which means I am injecting electrons in the n-type area and I am injecting holes to the p-type area. So automatically the number of electrons will increase in this side, and at the same time number of holes will increase in the p-type region. Right? Due to the accumulation of these charges, right, there will be, right, these will be actually pushing each other, right? This will push the depletion region towards the p-type, and the holes will push the depletion region towards the n-type. Hence, I can say that the depletion region will shrink, or it will get narrower, right? When I am increasing the potential, right, I could say that the depletion region will get narrower and narrower, right? At a certain point, for example, let the depletion region becomes small enough so that the electrons can jump from one side to another, right? Suddenly the electrons will started traveling across these depletion region, right? Or I could say that the electricity started flowing through the this PN junction, right? So if I draw the current versus voltage, right? This will be my voltage and this is my current, right? First, as I said, when I am increasing from 0, the depletion region will get smaller and smaller, which means while the depletion region is getting smaller, there will not be any current, or the current will be very less, right? So I would say, yeah, very small current, right, will be passing through the diode, or sorry, a PN junction, right? After that particular width is reached, right? So the width at which the electrons can jump from one side to another, right? A sudden increment or a rapid increment in current will be observed, right? This will be something like this. A rapid increase can be observed in your current voltage characteristics, right? Okay, so this, since we are connecting minus to minus and plus to plus, right, we would say, yeah, this is our plus voltage region, right? This is plus voltage region, and we call the condition as forward biased, right? Forward bias PN junction. Right, let's see what will happen if I change the battery other way around, right? Which means I am connecting minus to positive and positive to minus, right? Okay, let me draw the PN junction again. Right, so we will have a depletion region where you have no charges, and then at N type you will have, yeah, more number of electrons and a few thermally generated holes. In the other way around, at P type, you have a lot of holes and a few electrons. Right now, under reverse bias, what I am doing is I am connecting N type, or the minus terminal, right? Right, minus terminal to the plus terminal of the battery, and P type, or the to the minus terminal of the battery, which means I am introducing, or I am just withdrawing a lot of electrons, or in the other way around, I could say, yeah, this is plus minus. I'm giving a lot of free electrons here, right? And this terminal, which I am injecting a lot of free electrons the other side, and I am injecting holes in the N type, right? So I would say all these free electrons will recombine with the holes, and these holes will be filled with these electrons. Hence, I can say that the depletion region will, right, will grow or will get wider, right? So here in forward bias, it will get narrower, and under reverse bias, the depletion region will get wider, right? I would say when a hole is being filled with an electron, right, as seen earlier, there will be a minus ion being created, right? So yeah, sorry, a plus ion is being created, and then the other way around, when an electron is filling the hole, there will be a minus ion is being created, right? So due at these conditions, right, at these conditions, I would say this side, the majority carriers at p type is holes, but since due to the presence of these minus ions, these minority carriers can, yeah, diffuse through the wider reverse bias junction. At the same time, here at the N type, the holes can diffuse through the positive ion stack, and then they can combine at the interface again to make a electron hole pair, which is again a minus ion, right? So due to the migration of these minority carriers, there will be a very small current, right? A very small reverse bias current, which is from N type to P type, right? That is called as reverse saturation current, IS, right? Reverse saturation current, IS, right? Again, when I am keep on increasing the voltages, right, so that will be much less when compared to the other current, because the carrier concentration, the minority carrier concentration will be much lower, right? So when compare, so if I draw the other side, right, it will be a very small current, and this will be your IS, or reverse saturation region, right? And hence, why, because of I am connecting plus to minus and minus to plus, right? This is plus voltage axis, and this becomes minus voltage axis. And then since I have the current in the reverse direction, right? So the current is also in the minus I direction, right? So this will be your reverse saturation current. Right, now I am keep on increasing the battery, right? And then, sorry, the potential of the battery. Hence, the depletion region will get wider and wider, right? The depletion region will get wider and wider. At one condition, the whole semiconductor crystal, or the whole PN junction slab, will be occupied by the depletion region. And at that condition, I could say that, right, the PN junction turns into kind of a parallel plate capacitor, which has two potential across these two, and a dielectric material in the middle, right, which does not have any free charges which could contribute to the electricity, right? At that condition, if I increase the potential further, the electrons at the bonds, right, will get an energy which is E into E, right, where E will be the voltage divided by the distance, and then it will be pulled off from the bond, right? If this EE is sufficient enough to remove the electron from the bond, that will be removed, and it will be further accelerated by the electric field, and that accelerated electron will hit another electron at the bond, and now two electrons will be created, right? So kind of those two will be removed and accelerated, and they will hit another two, and then four will be created, right? Likewise, a carrier multiplication will happen, right? So this kind of a rapid process, right? This will be a rapid process once the voltage reached, right, where or which is sufficient to remove an electron from the bond. We could say that the diode is actually break down, which means the electrons can be pulled off from the bond, accelerated towards the other bond, and they can hit another one, and then they can multiply, right? At this condition, due to carrier multiplication, you will have a huge current, but in the opposite direction, right? You will have a huge current, or I could say that a reverse bias current, and this is called as VB, right? A voltage, or which means the diode is completely breakdown, right? And in normal PN junction diodes, this breakdown is not reversible, right? In normal PN junctions, this breakdown is not reversible, right? Once it is breakdown, then you cannot use the diode again, right? So this is the current voltage characteristic of a PN junction diode, and this is actually called as BB, or barrier potential, right? OVD we can make it as, and this could be B breakdown, right? B breakdown, BR, I would say, right? So this will be much higher than the barrier potential. For example, for silicon diodes, this will be about 0.7 voltage, and for germanium diodes, this will be about 0.3 voltage, while the breakdown potential will be higher than 25 voltage, right? So when compared to the forward or barrier potential, the breakdown potential is much higher, right? So I would say, yeah, I can put a break mark in the axis, right? But hence we will have a small reverse saturation current in the diode, right? So I could say, I could write the current equation through the diode. I equals I naught into, right? So exponential of, right? So maybe VT over, right, KT, right? Eta KT minus 1. Right, where D is the voltage across the diode, and then neta will be called as maybe an empirical constant, right, or an ideality factor or whatever, right? So an empirical constant, and KT, K is Boltzmann constant, T is absolute temperature, or we can write KT into VT, where temperature equivalent of voltage, right? So this will be around 25 or 26 millivolt at, yeah, maybe 26 millivolt at 300 Kelvin or 27 degree C, right? So this is the forward and reverse bias characteristic of a PN junction diode. So in simple words, I can say that, right? So if you apply a small region, the diode or a PN junction, right? This is the symbol of a PN junction, where this is minus, right? Sorry, yeah, this should be your plus, and this will be your minus, right? So the current will be conducted unidirectionally, right? If you apply plus to plus and minus to minus, the current will flow through the diode, and if you turn around the device, or if you turn around the power supply direction, the diode will be open, right? It will kind of an open circuit. So I could say that if you have a diode in a circuit, right, through that branch, the current will flow only in one direction, right? The reverse current is not possible, right? Because Is is much less when compared to the other currents, right? So yeah, we can see how we can use these diodes for an AC to DC converter, right? Or how we can use it for your to convert an AC current into a DC current in the next class.